Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue where we left last time. That is the algorithm for the overcurrent relay. Then we will see the types of overcurrent relays. Then we will have a look at relay coordination. Let us see how much we are able to cover in this lecture. Some part of relay coordination we may have to, including an example, we may have to look at it in the next lecture. After that, we will also have a look at earth fault overcurrent relays. So, this is where we stopped last time. The algorithm for the overcurrent relay. The first step is of course measuring the device current, which will be done through the CTs, which we have studied in the previous lectures. Then the ratio I by RF, which is known as the plug setting multiplier, which is a legacy from the term plug setting multiplier is a legacy from the electromechanical relays. The I by RF is usually done as a phasor calculation, but it could also be done on an RMS, plain RMS calculation as well. Then this is how the algorithm will look like. There are two counters. One is for introducing a weight so that no transients cause a tripping of the relay. The second one is a timer which is included if the relay operation itself has to be delayed. This is not an inherent counter, but a timer which is given to the user so that it can increase the time setting of the relay so that it can perform a backup function as well. What is a primary and backup function? We will have a look at in greater detail in the coming few slides. So, we will move on. This is the time multiplier setting. As we said, the timer is set using the time multiplier setting. There are two settings in an overcurrent relay. One is of course the current setting, as the name implies. There has to be a current setting in an overcurrent relay above which the relay will trip, or below which the relay will not operate. The second setting is the time multiplier setting. Not all overcurrent relays will have this setting, as we will see, but most of them do have this feature of time multiplier setting, or TMS. The earlier one was a plug setting multiplier where you set the current. In the time multiplier setting, or the time dial as it is known as in the American literature, you set the time setting. So, for the relay to perform a backup function, it requires a wait state. Backup means it is not we saw about zones of protection earlier. The fault is not in the primary zone of protection of the relay, but it is in the primary zone of some other relay. If that relay fails to operate for some reason, there are various reasons why the relay could fail to operate. It has not detected the fault properly, or maybe its TC supply is not correct, or could be an error with its CT, or so many other reasons why the relay does not operate. The primary relay does not operate. So, if it fails to operate, then you can't leave the fault hanging. So, there is a backup protection which is always provided. So, to delay the backup protection, because you have to always give the primary protection a chance to clear the fault first. Otherwise, what will happen is if the backup relay operates, it will remove more elements from the network than desired, and it is not an ideal situation that you want. So, to enable the primary protection to operate first, you give a time delay to the backup protection. So, it requires that the backup relay will wait for a certain amount of time before the primary relay, the backup protection wait for a certain amount of time before it operates. Now, what is this time delay? This delay is usually to the order of 250 to 300 milliseconds, and it is known as a coordination time interval. Okay, this is a part of relay coordination. That is why it is known as a coordination time interval. How did this 300 milliseconds come about? The relay, includes the relay operation time, the circuit breaker operation time, the reset time, and also if there are any errors associated with the CTs. So, 300 is usually associated with electromechanical relays. With numerical relays, you can reduce this to 250 to 200 milliseconds, but under no circumstances will you go below 200 milliseconds. Okay. Otherwise, you cannot guarantee that there will be sufficient discrimination or coordination between the relays. Okay, then maybe if you go below 200 milliseconds, there is a chance that the backup relay could operate before the primary relay. So, this delay is programmed or is set on the overcurrent relay by using the setting TMS or time multiplier setting. Time multiplier setting is defined as the ratio T by Tm, where T is the operating time of the relay for a given PSM, and Tm is the corresponding operating time at TSM equal to 1, or TMS equal to 1. Okay. So, relay operating time can be varied by varying the TMS setting. Also, of course, the PSM setting. So, if you vary the TMS setting, you can shift the relay operating curve, as we will see when we look at relay coordination. Okay. So, this is the figure for the inverse characteristics of a overcurrent relay. Now, why such inverse characteristics? One is because the fuse, as we have seen in the last lecture, has a similar inverse characteristic. So, if you need to coordinate the relays with the fuses, then this characteristic is useful. Also, this has a useful characteristic. This is a useful characteristic in its own right, because as you can observe, as the fault current increases, the relay operating time also reduces, which is what is desired. If for a longer, for a higher fault current, the relay operating time should be shorter. Higher fault currents can cause more damage, so they should be cleared more quickly. So, that is why this is a characteristic which suits the requirements as well. So, that is why it is a very popular characteristic to have. If you see the figure on top, this is a simple radial system here, and with, say, for a fault F1 or a fault F as it is shown here, this fault here, the relay R1 should operate first, but and the relay R2 and R3 are backup relays here. So, if you give a proper inverse characteristic and coordinate the relays, then this can be achieved. Now, as far as the classification of the overcurrent relays as far as the classification of overcurrent relays go, the first type of overcurrent relay is the instantaneous relay. Now, this instantaneous relay is used where there are where the faults occur very close to the source, or maybe in the primary of the transformers, etc., and it clears the fault very fast, or the action of the relay is very fast. It only has a pickup setting. There is no intentional time delay that is given for an instantaneous relay. So, it has no TMS setting and no time delay here. So, if you see here, if there is this source is a strong source and the impedances are also low in these sections, then the fault current will not vary much between the relays, between the sections 1, 2 and 3. Okay, the section 1 say is the section protected by R1, the section 2 is the section protected by R2, and 3 is the section protected by R3. So, there won't be much difference in fault current, and there you cannot have discrimination on the basis of fault current here. Okay. So, the relays R1 and R2 may see the same fault current. So, if you put instantaneous relays here, you cannot guarantee which one will operate first. So, and R2 is supposed to be a backup to R1. So, this instantaneous relay is not suitable for backup protection, okay, because you cannot where you cannot get discrimination in terms of current, which is in most of the places, you cannot use this instantaneous relay, and then that's why you have to go to the inverse kind of characteristics with a time delay. Okay. So, time delayed definite time relay, this is the second part. The characteristic is similar to that of an instantaneous relay, but here you can introduce a time delay. So, this can be used as for a short length feeders where the fault current does not vary much, and you need a primary and backup protection. These type of relays can be used. Okay. So, this is the characteristic of a inverse time relay. I will just draw the characteristics because there is no slide on those. So, I will just draw the characteristics of both instantaneous relay and time delayed definite time relay. So, if you have a look at the current versus operating time graph, this is the current and this is the time axis. The instantaneous relay is something like this. Okay. So, this is of course the operate region, and this side is the non-operate region. Okay. So, operate, this is the current setting that we talked about. Now, of course, though in theory or an ideal instantaneous relay should have 0 time delay and it should operate as soon as the current setting is reached. In practice, there will be some delay because there is processing delay, etc., that occurs, and that is why the characteristic even for a practical or instantaneous overcurrent relay will be something like this and not exactly 0. For a definite time relay, the characteristic is similar. It is of course not the same, it is similar, but there is a time delay which can be, this is the time delay which can be programmed or set. Okay. This is the current setting. Okay. So, this is the this is the non-operate region, and this is the operate region. Okay. So, the device numbers are IEEE device number 50 for this and 51 for this. 51 is also used for inverse time over current relay. I will just show you the device numbers. Just for your reference, you can if you Google it, you can get the device numbers as well. So, you can see here that 50 is an instantaneous over current relay, 51 is the inverse time over current relay. Okay. So, getting back to our slides. Okay. So, we looked at 2 types. The third is of course, we will have a look at the application here and of an time delayed over current relay, and then we will go to the inverse current characteristic. If you can see here, this it's the same, actually the same figure as we saw earlier, and here these are short length feeders, and the fault current does not vary much between the locations, because the impedances are also not very high, as they are very short. So, here the R1 will be set to operate without any intentional time delay. Then R2 will be set to operate at a similar level, but with a time delay of 1 CTI, as we saw earlier, that the relay has to be delayed by 1 CTI, or CTI as the coordination time interval. Now, R3 has to back up R2 as well, so it will be delayed by 1 more CTI. So, this also brings out a lacuna in this kind of overcurrent protection. Okay. Okay. Now, before we go here, I'll just since we have talked about the lacuna, I'll just mention it in brief. Now, for example, you have a long feeder with multiple sections, and say it is like this, okay, and there are relays here. Now, this, though I am drawing it like a circuit breaker, I assume that there is the associated CTP, PTs are not required in this case, but CTs, relays, etc., which operate the circuit breaker. So, there is R1, R2, R3, R4, R5. So, this R2 will be delayed by a CTA I, which is say 0.3 seconds in this case. Then this will be delayed by another 0.3 seconds. So, total operating time here we have got 0.6 seconds. Then this another 0.3 seconds, R4 another 0.3 seconds, which is 0.9 seconds here, and another 0.3 seconds, so 1.2 seconds. Okay. So, even if there is a fault here very close to the source, R5 will operate only after 1.2 seconds. Okay. This is not acceptable. You cannot allow, most utilities rather will not allow a fault to hang, as it is called, not being cleared for more than 1 second. Okay. So, this kind of relay coordination or relay coordination setup here is not acceptable. Does this mean that what we have said till now is wrong? No, it does not mean that. It also does not mean that this theory is wrong, or that what we learnt is wrong. It simply means that this kind of application is not suitable in this case. Okay. So, what you will probably need to do is for one section somewhere, you will have to use a pilot wire or a differential protection, say here in this section you use, say this is R5, R4, not necessarily use it here, but I am just for the sake of example. Then you can start the coordination afresh. Okay. This can be again set at instantaneous value, and then this will operate in 0.3 seconds. Okay. So, you have R2 and R1. So, this operation is 0.3 seconds, this is 0.6 seconds, then you break the chain sort of here, and then this again can be, no, this is R1. So, there is no instantaneous time delay, I am sorry, I made a mistake here. So, there is no this is instantaneous, so no intentional time delay. This is 0.3 seconds, then you break the chain here, then this is again instantaneous, and this was operating 0.3 seconds. So, this is, so the maximum that any relay has to wait is 0.3 seconds, and so this is how you overcome this limitation here. Okay. So, this we brought out a problem in the coordination. Again, for if we have only, say we had only definite time relays, okay, we did not have inverse time. Okay, then what would happen is, say this is the fuse at the point A, and then you have a relay close to the source, which is R1, and if a fault occurs in this section here, then you can have a problem, which is how we will just have a look here. Say this is the, we will draw the characteristics of both the fuse and the relay. The fuse has a inverse characteristic like this. Okay. And the relay has a characteristic like this. So, for currents up to this point, say, okay, the fuse will operate first, which is what we want, because the fuse is closer to the fault. But once the current exceeds this, you can see here that in this part that the this is the point A, and say this is I will not draw it like that. So, in this part you can see that the relay, this is the fuse. I will draw it again. Okay. So, this is the, here is the problem. This is known as a lack of coordination. Okay. To avoid this, then we would need a relay characteristic also of this form. Okay. So that we can have enough separation between the fuse characteristic and the relay characteristic. So, this actually led to the development of definite time or inverse definite minimum time relays, okay, with characteristics like there are various characteristics that are available, which we shall see soon. This kind of characteristic, okay, with varying kind of slopes. Okay. So, what these are and what are the equations governing those, we will see in our slides. Okay. So, we saw that there is a lack of coordination, and this led to the development of what is known as the IDMT, or the inverse definite minimum time relay. Okay. You can see that the characteristic is inverse, and as the current increases to beyond a certain value, it becomes almost asymptotic to the x axis. That is why there is a what is known as a minimum time. Okay. So, beyond a certain time, the relay will operate in I am sorry, beyond a certain value of current, the relay will operate in a constant sort of time, which is known as a minimum time. So, that is why it is both inverse definite minimum time relay. Okay. So, this is the most widely used character. Instantaneous is also used as backup for high fault situations, but otherwise the most widely used kind of relay is the IDMT relay. Okay. So, you can see three characteristics here. These are the IEC defined characteristics. This is the standard inverse, which is again in the IDMT, this is the most widely used. Then you have what is known as the IEC very inverse, this the second characteristic in red, and then the third characteristic in blue, which is the IEC extremely inverse. If you need to coordinate with a fuse, this is the EI, or the extremely inverse characteristic, is what will need to be used. Okay. So, now what are the equations governing these? Here you can see that the T is the operating time, TMS is the time multiplier setting, I by IS is the PSM, I is the current, and I is the measured current, and IS is the set current or the reference current, and these are some constants. This is of the form K divided by I by IS raised to alpha minus 1, and K and alpha values are given here. For a standard inverse characteristic, K is 0.14 and alpha here is 0.02. For a very inverse characteristic, you have K is 13.5 and alpha is 1, I by IS minus 1. And for extremely inverse characteristic, K is 80 and alpha is 2. There is one more which is known as long inverse, which is not which is very rarely used. That is why it is not listed here. There K is 120 and I by IS is 1. Okay, so but very rarely used characteristic. Now, one thing that you will notice here is that as the PSM goes close to 1 or I by IS goes close to 1, the denominator is very close to 0. Okay, so for that is why most manufacturers for electromechanical relays would not guarantee operation below PSM less than 1.5 or 1.6. Okay, because the time taken is extremely high, as you can make out from here, from any of these equations, and that is why the operation is not guaranteed. That is why the characteristic itself, if you see the characteristic, that will start at 1.6 or so, I mean close to that value. Okay, then I'm sorry, we went a bit back. Okay. The next set of equations is what are the IEEE standard equations. The earlier ones were the IEC standard equations. The IEEE standard equations are similar, but there is a slight difference here. There is a constant here which is there. So, even if however high the current goes, it will need this constant time here that is given this is 0.114 in the moderately inverse case, in the 0.491 in the very inverse case, and so on. So, here instead of TD instead of TMS, the term used is TD, which is time dial. So, instead of time multiplier setting, the constant uses time dial here, and there are 3 characteristics as in the case of IEC, which is moderately inverse, very inverse, and extremely inverse. Also 2 more, which is these are some old Westinghouse relays which were still used in the American system. So, even these are provided in the IEEE standard equations. Okay. So, as you can see, the nature of the equations is same except for some constant time which is there, but otherwise they are the same. These I forgot to mention that in the standard inverse there used to be in the olden electromechanical days there used to be a 1.3 second relay and a 3 second relay, but now with numerical relays that is sort of no longer relevant. One thing that should be mentioned here, that is that with these were the equations that were available, or these were the characteristics that were available with electromechanical relays. With numerical relays, this could be anything, K could be anything, alpha could be anything, and you could get whatever characteristics that you want. The trouble with that is if everybody starts having its own characteristic, then coordination would become difficult unless you are very sure of that characteristic. So, that is why in the interest of standardization these characteristics are still maintained. This is only purely from a standardization and coordination viewpoint. There is no other limitations. In a numerical relay you could program any value of K and alpha. Okay. So, these are the IEEE standard curves. So, they are quite similar to the IEC curves, but of course, there will be some minimum time as the time constant that has been added there. So, this depending on the application, whether you are using it for a American based client or a European or an Indian client, you will have to choose the relays. Most numerical relays will give you a choice of characteristics, and you can apply any characteristic that you find suitable, which was not the case of you didn't have flexibility like this with electromechanical relays. Okay. So, now how do you set the relays and how do you coordinate the relays? We come to the second part of setting of the overcurrent relays. The first one was of course setting the plug setting multiplier and the time setting as per the requirement to clear the fault, but you have to now take care of some other aspects also which we will go through. Okay. So, coming back to the classification, there is one more type of classification depending on the fault classification. So, we have seen faults that involve the ground and faults which do not involve the ground, line to line fault, line to line fault, that is the three-phase fault. Those faults do not involve the ground, whereas a single line to ground fault or a double line to ground fault will involve the ground. Now, for complete protection, this again this has reference to the electromechanical kind of relays. You require, these are the phase relays, the relays that are there in the individual phases are known as the phase relays, and there is one more element which is connected to the neutral CT is known as the earth fault relay. So, why this is required we will come to very shortly. Now, these 4 elements would provide complete protection, but generally if you had only 3 also, 2 phase relays like for example, this relay and this earth fault relay, also you could get complete protection. Okay. These two would, the phase elements would provide protection for 3 phase and line to line, any 2 line to line ground faults, any of the 3 line to line ground faults, any of the 3 line to line faults, and this relay, the earth fault relay, would provide protection for any ground faults also. Now, why do you require this? Because it is not that the phase elements will not see the ground fault, they will see, but the ground fault current, because there could be impedance associated with the ground fault, and there normally is, something touches the line or some tree touches the line or something. So, it could be a very high impedance ground fault, in which case the fault current could be less than the normal load current, and which means that it is much less than the setting of the phase relays. Okay. But though it is less than the load current or the normal full load current, it is still a fault, because there is still current flowing to the ground. It could lead to some damage and fire and etc. So, it has to be cleared. So, you need a sensitive earth fault or a zero sequence relay, and that is why this an earth fault relay is also provided along with the phase relays. We will see earth fault relays in a slightly more detail in the next lecture. Now, coming back here, this is the kind of setup that you would require in a electromechanical relay type. However, in a numerical relay, you can, it is simply the earth fault, because you have all the phase currents. You can have 3 I naught equal to IA plus IB plus IC. You can do this programmatically in the numerical relay. So, you may not require this earth fault relay as a separate relay in a numerical relay. It may still be provided, because it provides a backup function and it avoids a single point of failure, etc. That is a matter of reliability, but in this case as a relay, it is strictly not required. Okay. So, these are some guidelines that we have for setting of overcurrent relays. Okay. Now, the first one is quite obvious, that the pickup current should be above the maximum load current, because otherwise it will pick up for load currents and then maybe cause some kind of nuisance tripping or something. Now, the thing to keep in mind is most electrical equipment are rated for some kind of overload. Okay. So, usually this is 10%, that is an equipment which is rated for say 100 amperes can operate at 110 amperes continuously, that is for 24 hours, which is also known as 24-hour rating, or a motor which is rated for 40 kilowatts can operate at 44 kilowatts, etc. So, nobody will actually deliberately load it, but this the equipment can withstand about 10% overload on a continuous basis. So the pickup value should be above that also. So usually it is set at 120 or 130% to take care of these normal overloads also. Pickup current should be below the minimum fault current. This one is also quite obvious, because otherwise if the pickup current is set above the minimum fault current, then it will not pick up at the lowest levels of fault also. So your pickup current should be somewhere above the maximum load current, that is above say 120 to 130% of the rated load current, and maybe somewhere below the minimum fault current. So you usually get a band to set your overcurrent relays. Okay, and where to set it will depend on many factors. That is why relay setting is also known as a art and not a pure science. Okay, so moving on, the pickup current should be below the minimum fault current, not only of the section that it is protecting, but also of the section that it is backing up. Okay, so this is also important. It may be a little confusing to note right now, but we will see it with an example, and that should make things very clear. Okay, so the second thing is that is the current setting. The second thing is the time setting, that the backup relays should also provide enough time for the primary relays to operate. So in other words, they should be delayed by a time known as the coordination time interval. Okay, so what are the primary and backup relays, and how do we set them? We will of course see it with an example, but before that we will have a look at what the primary and backup relays are, and then how do we go about setting them. Here in this figure, if you see these relays here, actually this shows a coordination tree. This doesn't show the feeder diagram, but it just shows the nodes here, and the nodes means that there are relays also at the nodes of those feeders. So relays 6, 7, 13 and 12 are the leaf nodes. So these are the relays that you will set first. Okay, then you look at parent-child relationships. 4 is the parent of 6, 5 is the parent of 7, 10 is the parent of 13, 11 is the parent of 12, and so on. And similarly, you can you have to go one level up each time. So so 3 is the parent of 9, and so on. So you have to move up the tree till you reach the source. So in this case, the relays at the leaf nodes will be set first. Okay, and then the parent nodes are the backup nodes for each child node. Okay, so then those will be set and so on. But first, the first step in any coordination is the identification of the parent and child. Okay, so if you see the some of it is quite clear, but if you see 1 is the parent of 2 and 3. So unless 2 and 3 are set, 1 cannot be set. Okay, so which is sometimes a bit complicated, because you cannot once 6 is set, you can set 4. Okay, but you cannot set 2 after 4 directly, because you have to set 5 and then you have to set 2. Okay, in this case also, if you see 3 is the parent of 8 and 9. So once 12 is set, then 11 will be set, then 8 will be set, but then you have to wait for one more till 9 is also set, till you set 3. Okay, so all this parent-child relationship has to be properly considered and maintained. Okay. So we will see an example here so that it is clear. We will see a numerical example also in the next class, which will make things even clearer. So now if you see here, these are the this is of course a different example, but this is a different example, and you can see that the the feeders and the branches of the feeders here. So, the relays R1, R2, R3 and R4 are the leaf nodes. Okay, they are protecting the sections 10, 13, 11, 12, 7, 16 and 6, 15 respectively. So, these will be set first. Okay. Oh, I am sorry, I missed R3. R3 will also be set first, okay, because they are the leaf nodes. Now, once you complete setting these, then the backup relays will be set. Okay. So, the red relays are the relays being set. Okay. So, now the parents of R2, the parent of R2 is R7, so that will be set. Parent of R1 is R6, so that will be set. Parent of R5 is R9, that will be set, and R4, R6, that will be set. Now, the parent of R3 is R10, so that will be set. Okay. Now, because R10 is set, you cannot set R14 directly, because the relays 12, 11, 12 and 13 have still to be set. So, once that is done, only then you can set R14. So, then in the next step, R11, 12 and 13 will be set. Okay. So, once R10 is already set, now in this step R13 has been set. So, in the next step R14 can be set. Similarly, R11 and 12, in that there is no doubt, because the two feeder branches are very similar. Okay. So, in the next step after that, now all 10, 11, 12, 13 have been set. So, we can go ahead with setting 14 and 15. That I am dropping the R, but when I say 14 and 15, I mean R14 and R15 can be set. In the next step, that is the last step, this is the source node. So, since both 14 and 15 are set, R16 is also set. So, this completes the setting or the coordination. Okay. We will have a look at the algorithm, because we discussed in words, but we will have a quick look at the algorithm, and then we will set up the problem. Maybe we will go about how to solve it the next time in the next lecture. So, this is the algorithm. You have to first initialize the coordination tree. Then are there any leaf nodes except the root? If yes, then go to the step 3. Step 3 is this step here. You have to identify the leaf nodes in the coordination tree. Then the PSM, that is the current setting of these leaf nodes, have to be set first. Okay. Then what are the parents of the leaf nodes in this step, this particular step 3 here? What are the parents of these leaf nodes? Then the PSM for those and the TMS for those have to be set. How the TMS is set is, first you find, once the leaf nodes are set, you find the operating time, you add the CTI to that, and then set the TMS for the backup protection. Then you delete the leaf nodes and then go back to step 2 and iterate this process till the coordination activity is completed. Okay. We will see it with a numerical example. So, in this part of the lecture, we saw the limitations of fuse protection. We saw the fundamental principles of the overcurrent relay. We saw what are the settings, that is the plug setting. The current setting is known as the plug setting multiplier, and the time setting is the time multiplier setting. Then what are the types, the instantaneous, the definite time overcurrent relay and the inverse definite minimum time relay. Then how the primary and backup relays function and how they are set, and finally the coordination. We will have a quick look at the problem, and then stop for the day. Okay. So, we will see with an example here. This is the example of a radial system. You can see that there are 5 buses here, and the source is at bus E. The remote or the leaf here is at bus A, and the loads, individual loads at each section are given. So, the section BA sees a load current of 50 amperes. The section CB sees the load current of 50 amperes plus the next 50 amperes also flows through the sections CB. So, this will see a load current, R2 will see a load current of 100 amperes. Similarly, R3 will see a load of 200 amperes, and R4 will see a load of 250 amperes. Okay. So, here we have chosen pickup current should be above 1.2 times or 125% of the maximum load current. As I said, you usually choose it to be above 110%, could be 120%, 130%. Here we have chosen 125%. You could choose somebody could choose 120%, somebody could choose 130%. We have chosen here 125%, and all of us could be right. Okay. So, it's not that this every time you have to choose 125. You have a lot of flexibility to choose the pickup currents here. Then the second aspect that we discussed was that the pickup current should be less than the minimum fault current also. So, here we have chosen again a value of 2/3 of the minimum fault current. It could be anything, you could choose it 20% less or 3/4 or whatever that your experience and your reading of that situation there tells you. Okay. So, here and the backup protection is provided by the time discrimination, not by any current setting here. Okay. So, we will have a quick look at this table here. This just for reference, these are the relays R1, R2, R3 and R4. R1 is seeing 50 amperes load current, R2 is seeing 100 amperes load current, R3 is seeing 200 amperes and R4 is seeing 250 amperes, which is what is listed here. So, MXFL is the maximum full load current. This is the minimum pickup on load current. These are the minimum fault currents. You will have to do some kind of short circuit calculation to find the minimum and maximum fault currents. The fault currents could vary, there are some generators are in, some lines are in and out and all that. So, that is why you can get a minimum fault current and a maximum fault current. Or if the load is the same throughout the day and nothing is changing, then minimum and maximum fault current would be the same. So, the third column, or rather the fourth column here, the minimum FC is the minimum fault current on the remote bus. Okay. So, the fifth column here is the maximum pickup current here, that what we could set it here. Okay. And this is the maximum fault current. As we see here, there is a variation between the minimum and maximum values of fault current, 250 to 500, 650 to 1200 and 1100 to 2000, 1600 to 3500. So, this is the minimum fault current here, this column here, and this is the maximum fault current. Okay. This is the PSM and this is the TMS. So, we will just have a quick look here. Now, we have what we have said is the minimum pickup current should be 125% or 1.25 times the maximum full load current. So, which is 62.5 in this case, 125, that is 1.25 into 100, which is for R2 it is 125, for R3 it is 250 and for R4 it is 312.5 amperes. These are in amperes. Okay. Now, the maximum pickup current, which we are saying is should be 2/3 or that of the minimum fault current. Okay. So, here in this case 2/3 of 250 is 167. So, for R1 it is 167. Now, keep in mind that for R2 it is not 2/3 of 650. Okay. It is not the maximum pickup current for R2 is not 2/3 of 650. Why is that? Because if you set it at 2/3 of 650, which is 433 amperes, then it will not pick up for the minimum fault current which is there in the section, this section here. Okay. Keep in mind that R2 has to act as a backup for this section also. So, the minimum fault current here is 250. If you hit this at 433 here, which is 2/3 of 650, it will not see this fault current at all and it will not act as a backup relay. Okay. So, to avoid that, we set it at 2/3 the minimum fault current of the section that it has to back up. So, it will be 2/3 of 250. So, for R2 the maximum pickup current is 2/3 of 250, which is 167. For R3 the maximum pickup current is 2/3 of 650, which is 433 amperes, and for R4 the maximum pickup current is 2/3 of 1100, which is 733. Okay. So, this is the relationship, because this R2 backs up the section protected by R1. So, here it is like this, and okay. So, this is how you will do it. Now, what do we set it at? Now, we have a choice of setting the pickup between 62.5 and 167. Okay. This is the minimum pickup current, this is the maximum pickup current. So, here we have chosen 160. Okay. You could, as we said, you could choose anything. Why 160? There is no one answer to this. You could choose it at 150, you could choose it 165, 167. If there are 100 students doing this, we could have 100 different answers and all of us could be correct. Okay. So, that as long as you do the rest of this coordination properly, all of us could be correct at the same time. Okay. So, there is no one right answer. We have chosen 160 and the minimum setting in TMS setting in this relay is 0.025. Okay. So, here for the first section we do not take any intentional time delay. So, we take the minimum time setting that is available, and this is how it is set here. Okay. After you take this is how it is set for a TMS of 0.05 and a standard inverse curve. This is how the relay characteristic will look like. Okay. And then for the maximum fault current that the relay sees, which is 500 amperes, you find the operating time of the relay. Okay. Find the operating time, add the CTI, and then use that as a TMS for relay 2. Okay. We will stop here and continue with the coordination with relay 2 and 3 and 4 next time. Thank you.